Hello, everyone. Welcome to this episode of QuEra's webinar series, Science with QuEra. This webinar is designed for the technical and scientific members of the quantum community, providing a rare opportunity to hear directly from QuEra's researchers. This is part of several webinar series that QuEra hosts, so I would encourage you to sign up for our newsletter on our website, follow us on LinkedIn to stay informed of the different opportunities to engage with the QuEra team. Also, this is the 9th episode as a part of this series, and so if you find today's content interesting and relevant to your work, I encourage you to go to our YouTube channel where we have all of the past webinars hosted for you to view. Today we're joined by Zhou, who is a research scientist at QuEra and Harvard University and the lead author on two papers, including one that was recently published in Nature on a new low overhead transversal architecture. And so Harry's going to walk us through some of that work. Before we get into that, I'm going to give a brief overview of QuEra for those of you who are potentially newer to our company. And then at the end, time permitting, we'll have some time for Q&A where you can ask Harry questions directly related to his work. So please do use the Q&A functionality in the webinar here, as we won't be using the raised hand feature. So with that, I'll dive in with a little bit of an overview of who we are at QuEra. So QuEra is a quantum computing startup that was born at Harvard and MIT. Our scientific co-founders, our four scientific co-founders who are still actively involved in the company today, two of them came from Harvard and two of them came from MIT. We still work very closely together with both of these universities through the form of sponsored research agreements. We have some QuEra hardware in both of those labs that the teams are actively using. We consider ourselves the technical and commercial leader in neutral atom platforms. We think this is one of the most promising modalities in quantum computing. Apologies, my slide keeps automatically advancing here on me. We have systems available on-premise and in the cloud as well. And we recently raised $230 million in our Series B round earlier this year, which is allowing us to move our our scientific advancements from our academic partners into commercial opportunities. We believe that neutral atoms are the most promising quantum architecture for two reasons. One, we think that the architecture supports error correction. First, we believe that value from quantum computers will come from fault-tolerant systems. And so as a result, we're designing our systems along with quantum architectures from the beginning. Some of the things that support that error correction is high parallelization across both the movement of our qubits, which are reconfigurable, and from the operations on our qubits. We also believe that these systems are going to be well suited for commercial deployment at scale. So our systems are modular. They have a small physical footprint. And part of that is the result of the no need for cryocooling, which also supports our very low energy consumption. And so together, we believe that these features are going to support the delivery of large-scale fault-tolerant quantum computers. Today's presentation, along with a lot of the work that happens at QuEra, is focused on error correction. We are deeply focused on both the theory behind error correction, but potentially more importantly on the demonstration of that work as well. And we learn a lot from the demonstration of that theory, and we use that to inform the way we build our future systems. We call that design, or we call that process co-design. And so I'll just briefly talk a little bit about where the work that Harry's going to discuss today fits into our broader error correction strategy. And you know, at the foundation of what we're doing here comes from the fact that we have proven the fundamental quantum error correction capabilities on the neutral atom platform. This work was a seminal paper published, led by Harvard, with support from QuEra and other academic institutions. This was the first experimental demonstration of a logical quantum processor. Took advantage of computer's high parallelization and a multi-zoned architecture. First time we saw storage, compute, and readout zones within a quantum processor, and it's really paved the way for the quantum error correction work that came after. Earlier this year on our Gemini class system, we were the first company to experimentally demonstrate magic state distillation, a process that is critical to executing error correction at scale, but also providing universal functionality of logical operations. We also, and we'll dive a little bit more into this today, we've also focused a lot on not just proving these concepts out at very small scales, but actually modeling the work that we're doing out to large-scale architectures to ensure that the error correction techniques that we're designing into our systems truly are scalable. And lastly, and kind of goes hand in hand with this scalability concept, we've focused a lot of time over the last several years on reducing the time and space requirements for error correction. You see this first paper on the left here is focused on a scheme that allows for constant quantum resource overhead as these error correction schemes scale. In the middle, you see an example of some recent work focused on the classical overhead required to execute quantum error correction at scale. It's increasingly becoming evident that error correction and fault-tolerant systems are going to be a combination of HPC resources for things like decoding, and then, of course, the quantum resources for the computation itself. And so we're equally focused on both sides of that. And then lastly, we'll talk a little bit about the low overhead transversal architecture, which is also a critical step in improving the efficiency of that quantum overhead. And so with that, I'll hand it over to Harry, who will talk specifically about these two building blocks in our broader error correction strategy.
Yeah, thank you very much for the nice introduction. So I'll share my screen now. Yeah, can you see it well? Okay, great. Yeah, so today I'll be telling you a little bit about our recent work on low overhead transversal architectures for reconfigurable atom arrays. We'll be covering these two papers, this recent Nature publication and this ISCA paper, which is was accepted earlier this year to a computer architecture conference, where we also lay out the implications of these architectures in terms of the large-scale resources. I should mention that a lot of the first half has also been covered in a previous webinar that my colleague Chen gave. So feel free also to check out that recording as well. I will be going a little bit faster over that part because of this. So as we think about the promise of quantum computers, there's of course many potential applications of them across cryptography, chemistry and simulation, and optimization, but we don't really have these utility scale quantum computers quite yet. So what is the reason for that? Well, a large part of it is that combating errors is really the core challenge of making large-scale quantum computing happen. More specifically, if we look at the physical error rates that we have today, somewhere between 10 to the minus 2 to 10 to the minus 4, and what these large-scale algorithms seem to require, something on the order of 10 to the minus 12, there's a very big gap which needs to be bridged by the methods of quantum error correction. And so really, a large part of the field is asking about more efficient methods of bridging this gap so that we can use moderate amount of resources while being able to execute very large algorithms. If we look at some of the early estimates, for example, from this paper from the Microsoft team, you'll see numbers like this. So for example, if we take 100 microsecond gate, 100 microsecond measurement, something that is fairly typical for a neutral atom system, you'll see that large-scale factoring would take something like, on the vertical scale, several years and 30 million qubits in this particular estimate, which is prohibitively large and also prohibitively long of a runtime. And the main reason for this is that the logical clock speed here is a lot slower than the physical clock speed. And so here we're really developing methods that allow us to substantially bring that down by making use of transversal fault tolerance ideas, by making concrete layouts respecting locality and improving the movement and decoding complexity, and also finally backing this up with further logical error rate models and optimizing the algorithmic parameters of the compilation based on those considerations. And the final result is that we're able to get things to execute now within around a week or so runtime, rather than the several years that previous analyses of such platforms would seem to assume. Okay, so first I'll tell you a little bit about our transversal fault tolerance constructions, since that underlies much of the resource estimations that I'll be telling you about. So to think about this logical clock speed being a lot slower than the physical clock speed, of course, we first want to understand where that arises from. And the reason that this occurs is because when we try to measure so-called stabilizers or syndromes, which allow us to catch what qubits may have had an error, these stabilizers themselves are also noisy. So not just the data qubits are noisy, but the stabilizer measurements are also noisy. So if you look at the stabilizer, it might be quite unsure about what it's concluding. And for this reason, standard fault tolerance constructions tend to require repetition, in which you perform the syndrome extraction round order d times to gain confidence about the stabilizer value. So you basically repeat, and then you do some type of majority vote like looking thing to allow you to correctly deduce what error actually occurred. Now in practice, this code distance is somewhere between 20 to 30 in these larger scale problems, which means that there's a very significant speed logical clock speed reduction of 1 to 2 orders of magnitude compared to the physical clock speed. And so it's this type of order D repetition overhead that really is challenging and really we want to reduce upon. So the idea that we had, very much inspired by the experiments that were being run in the labs at Harvard and at QuEra, is instead of thinking about each individual block and trying to gain fault tolerance through repetition there, you can instead decode the logical qubits jointly in space-time, and the syndrome extraction on different qubits can actually help each other out. And so by taking this holistic end-to-end view of fault tolerance, we actually find that instead of performing order D rounds, this order D intuitively, this error correction load can be spread between the different logical qubits. And for each operation, you actually only need order 1 syndrome extraction rounds. So this was a realization that we had, but one of the key challenges that we needed to address is how to make it work for mid-circuit measurements and feed-forward, which is very important if you want to execute a general universal quantum computation. So here what we're seeing is you have some circuit, you have some Pauli initial states and some magic state inputs. The magic states are prepared fault tolerantly through some cultivation or distillation procedure. And then following that, we run a transversal Clifford circuit, which basically executes the Clifford operations. And then in order to perform non-Clifford gates, we use this teleportation procedure with a mid-circuit measurement and a Clifford feed forward. So in this case, one of the concerns that one might have is when you're interpreting this logical measurement, naively, it might seem that you don't have full syndrome information on these other logical qubits, which might cause a challenge in interpreting this. And indeed, the previous intuition that people had was that if you had order 1 syndrome rounds during state preparation, then maybe the new syndrome information might actually cause the assignment of these logical measurements to change and thereby screw it up. What we observed is that actually the Pauli initialization errors that people are worried about, which people are worried would change these measurement results, they actually, because they're a Pauli state, there's a known stabilizer. And so these Pauli initialization errors actually do not change the measurement distribution. In other words, when you apply the Pauli, you're permuting these bars, but if you look at the distribution of measurement outcomes, it actually still remains the same. And so if we look only at the degrees of freedom that actually are relevant, namely certain logical Pauli products that we need to reliably decode, then actually just looking at those, we can reliably decode these logical measurements in a way that that is always consistent and always done correctly. And this is analyzed in more detail in the paper. I encourage you to check it out, and also in the follow-up paper together with our collaborators at Harvard and our team at QuEra. And so with that, the conclusion basically is that in this setting where we're preparing magic state, where we're preparing magic states fault tolerantly through this cultivation and distillation procedure, the Clifford portion that we're executing here, every Clifford gate actually only needs to have a single syndrome extraction round following it. And so with this, then we wanted to proceed and see what the implications of this really are when we lay out a complete algorithm. In this case, we'll take one of the standard things that people tend to look at, which is this Shor's algorithm as a prototypical example for this analysis. So to compile an algorithm, what we do is we basically take the initial algorithm that we're interested in, we break it down into algorithmic building blocks, such as arithmetic or table lookups, rotation synthesis, magic state preparation. And we, in turn, for each of these, lay out a transversal block implementation such that we can efficiently implement it. With all of these gadgets, they become a parameterized model based on your parameters of your algorithmic compilation, and we can then balance the resource usage and optimize the layout in order to get the final result. So Shor's algorithm proceeds as follows. Essentially, it's running period finding on this g to the x function, and the period that you have, g to x mod n, and the period that you have will essentially manifest when you try to do phase estimation on this function. So the procedure, we're using this iterative phase estimation procedure in which we do controlled modular exponentiation up to some exponent. And the dominant cost when one lays it out is this controlled modular exponentiation. So what we want to do is to break it up into arithmetic routines, following the approach pioneered by Craig Gidney and Martin Nichera. So what we do is we essentially decompose the exponentiation into multiplications, which in turn decompose into additions. And we perform windowed arithmetic, which breaks this big multiplication or addition into multiple smaller pieces that are partially done on a classical computer via a table lookup. So what we'll be doing is we build up each of these subroutines at the bottom layer and then gradually go up to build up the entire stack, where each of these individual subroutines are informed by the transversal architecture that I described earlier. So I'll first start with the bottom layer. I'll focus primarily on the magic state part in the interest of time, since the webinar is relatively short. So here what we do is we first prepare magic states via magic state cultivation procedures that came from Craig Gidney from Google. We utilize this procedure in a way that we end up in surface code patches. And then we, because the logical error rates aren't quite good enough for the factoring application, we then utilize an 8T gate to CCZ factory to refine this into high fidelity CCZ states for the actual consumption. The layout of the factory is found using code from our collaborators. This is an open source package that you can also use in order to identify an efficient factory layout that also works in one dimension. With that, we also work out similar things for CNAR fanouts and for methods to perform parallelization. And so then we can proceed on to the actual algorithmic subroutines. I'll just walk you through again one of the key subroutines that we look at here. So here we're looking at a quantum adder, which has this ripple carry structure where you're taking the majority of the output in each of these individual steps. And then finally, on the way back, you do this majority operation. So for this type of layout, for this type of algorithm compilation, what we see is that we really just need to be able to efficiently implement each of these blocks. And so what we do is utilizing ideas such as auto CCZ corrections that people had in the literature. We find an efficient layout which only performs very local move, thereby making sure that the actual movement time doesn't become too large. And then each step is again using this single time step transversal operation. So we prepare these CCZ resource states that I mentioned earlier. they come and interact with the qubits in a certain way, and then we perform some Clifford corrections for the feed forward. We also similarly lay out the table lookup procedure, and in total, we can then look at the overall sizes that we actually need. So for example, this is what our rough layout looks like during the lookup phase and the addition phase. You'll see that because the addition is happening bit by bit, the active addition area is actually quite small, and a lot of the footprint is dedicated towards performing magic state distillation. All of these, again, relies on making sure that the interaction is relatively local, which is a nice feature that happens within this particular compilation. And this has two benefits. One is, of course, that it minimizes the movement distance, which reduces the amount of time that we need to spend. We're explicitly accounting for all of the times that each step needs to take based on the movement distance. But another thing that happens, which I think also goes to one of the questions that was asked in the chat, is that the relevant decoding volume in this case grows only linearly. Essentially, you have a linear light cone that is going out. So it still increases somewhat compared to, say, a regular decoding problem in which you're just decoding a single logical qubit for d rounds. But because this relevant volume is growing linearly, it actually, in the end, doesn't blow up the volume too much, particularly considering that also we have a little bit more of a time budget given the neutral atom platform with a slightly slower per step operation time. We also separately developed methods to reduce the decoding problem still into a matchable problem for the surface code case. So with these, we're pretty optimistic that the decoding problem, while a little bit more complex, is still very much under control in this type of procedure. And so the final part that I'll quickly mention is just how we put together the logical error rates and how we try to perform a heuristic estimation of the overall resources for carrying out this algorithm. So if we think about quantum error correction, really another thing that we learn in terms of intuition from our earlier transversal fault tolerance work is that it's really a battle between the addition of entropy into the system via just the noise that is naturally happening and the extraction of entropy via syndrome extraction. And so if we perform syndrome extraction, then we essentially want to sit somewhere in a place where we're balancing the cost between the amount of entropy that we're adding in and the entropy that we're taking out. So we can formally write that down in terms of how much the space-time cost is. You essentially have a space-time volume that is increasing as you add in more syndrome extraction. And then depending on how frequently your syndrome extraction is, you basically might need to handle more noise within this time if you did it less frequently. And so we can encapsulate this with a heuristic formula as shown on the bottom right here. And we can then, using this, heuristically look at the scaling as well as fit it against numerical simulation data. What we see is that indeed performing, depending on the detailed error rates encapsulated by this lambda factor, which is how much the logical error rate decreases as you increase the code distance by 2, as well as a factor encapsulating how much decoding gets harder as we go to these more complex algorithm settings. We see that overall, the number of syndrome extraction rounds still sees a minimum space-time volume when we're sitting at around 1 round per C0, maybe a little bit less than that for common operation regimes, giving us confidence that indeed we should be able to do a single syndrome extraction round per C0. And so that's what we'll be using in the subsequent analyses. And so what we did was we basically went through this whole procedure of compiling things, of estimating the logical error rates of each gadget, balancing their layout, as well as the sizes of each thing, the code distance. And then in the end, what we get is this significant reduction compared to the standard compilations based on lattice surgery, where we're able to significantly reduce the runtime down from several years to something that is a week or so, without increasing the physical qubit footprint. Of course, since our work, there's been great work coming out from other people, also significantly reducing the number of qubits involved. And so that's something that we're also interested in incorporating and exploring in future work. So with that, I'd just like to thank my collaborators who did a lot of the work together with me. So in particular, Chen, Dolev, and Maddie were instrumental in really developing a lot of the ideas associated with transversal fault tolerance. And then the resource estimation also had a lot of help from Casey. So with that, thank you for your attention, and I'm happy to take any more questions.
So Harry, we had a question in the chat. How does this physical qubit requirement translate to logical qubits?
Yeah, so I don't remember the very specific numbers of how many logical qubits this eventually corresponding to. For the program itself, I know that it's 6,000 logical qubits, so it's 3 times n, where for 2048 the n is 2048. And then I think we're using additional auxiliary space that is comparable because of the magic state preparation. So I think it comes down to around 10,000 logical qubits or so being assumed here. But of course, with recent improvements, both in LDPC codes as well as these yoking ideas, the ratio, the number of logical qubits would stay the same, but the physical footprint usage can probably be brought down. Yeah.
Okay. I think with that, we can end it. Harry, thank you so much for your time. And we look forward to seeing all of you at the next Science with QuEra webinar.
Thank you. Thank you everyone for coming.